So what if the secret to building truly smart AI isn't about making our computers bigger and bigger? What if it's actually about reverse engineering the only real intelligence we've ever known, the animal brain? That's what we're digging into today. A whole new frontier for AI that's looking past just scaling up and instead looking into the very blueprint of thought itself.
All right, so here's the game plan. We're going to start by looking at why the current approach to AI is hitting a wall. Then, we'll explore the brain as a kind of blueprint for a smarter way forward. After that, we'll get into the wild methods scientists are using to actually copy that blueprint, see where they test these new digital minds, and finally, we'll talk about what all this could mean for the future of intelligence.
For a while now, the big idea in AI has been pretty simple. Bigger is better. The scaling is all you need hypothesis. The thinking is that to get smarter machines, you just have to throw more and more data and more computing power at the problem. And hey, let's be fair, this has given us some pretty incredible stuff.
Now, on paper, this totally works. I mean, a big enough network with enough data can, in theory, learn anything. But in the real world, we're starting to see the cracks. The sheer amount of data you need is becoming astronomical, and this whole approach kind of falls flat when we try to build agents that need to see, move, and actually interact with the world around them.
And this isn't just some abstract idea. As AI researcher Aran Nayebi says, scaling all by itself just isn't a practical way to get there, especially if you want the flexible, general kind of intelligence we see in nature. It's a piece of the puzzle for sure, but it is not the whole picture.
So, okay, if just making things bigger isn't the whole answer, where do we look? Well, turns out we have a pretty amazing model to work from. In fact, it's the only working example of general intelligence we have, and it's been fine-tuned over billions of years of R&D. We're talking about the brain.
Okay, so think of it like this. That massive pre-training that goes into a large language model, you can see it as a kind of shortcut. It's like we're trying to cram billions of years of evolution, all that slow learning that gave our own brains such a great head start, into just a few weeks or months of computer time.
But here's the thing. Evolution didn't just give us a big, messy glob of neurons. It built a super-structured modular system, right? You have one part of your brain for grammar, another for recognizing words, another for moving your mouth to speak. They're all separate modules that work together. And that, right there, is a key piece that's missing from most of today's AI.
So it seems like we actually need both ingredients. You need that initial evolutionary kickstart from all that training data, but you also need to build it into the brain's clever modular architecture. That's how you get agents that can really learn and adapt on their own throughout their lives. It's about combining the raw power of scaling with the elegant design of nature.
Okay, so if we need to copy the brain's architecture, that raises a pretty massive question. How in the world do you even start to reverse engineer the most complex object in the known universe?
Aran Nayebi has a great way of thinking about this. Imagine trying to figure out how your computer works, but the only tool you have is something that can measure the voltage on its billions of tiny transistors. That's pretty much the challenge neuroscientists are up against. It's like trying to understand a whole symphony by just listening to one violin.
So how do they do it? It's kind of a three-step dance. First, you record what a real brain is doing while it performs some task. Second, you build an AI and train it to do that exact same thing. And then, step 3, the moment of truth, you compare how they both work on the inside. If those internal activity patterns match up, you might just be onto one of the brain's secret algorithms. And to get the full picture, researchers are studying a whole range of animals, everything from fruit flies to mice and monkeys. Each one gives us a unique peek inside. One of the most amazing models, though, is the zebrafish larva. Get this, its skull is literally transparent, so scientists can watch its entire brain light up in real time as it swims around. How cool is that?
But brains are messy. No two are exactly the same. So how do you know if your AI model is a good copy? Well, the goal is something you might call a neuro-AI Turing test. The point isn't to fool a person into thinking the AI is human. No, the goal is to make an AI whose internal workings are so similar to a real brain that another biological brain is no more or less similar.
All right, so you've built your AI brain model, and you're ready to test it. You can't just plug it into a super expensive, fragile robot that could fall over and break, right? So, where do you go? Well, for these researchers, the answer is simple. You go virtual.
Simulation is basically the ultimate playground for developing AI.
You can fail fast without any real-world consequences. You can control every single variable, which is perfect for good science. And you can model any kind of body you can imagine. Best of all, a lot of the experiments being done on real animals are also in virtual reality, which means scientists can create a perfect digital twin of the experiment to test their AI models in.
To give you an idea of how powerful this all is, check out this experiment. Scientists trained monkeys to play a version of the old video game Pong, but there was a catch. Right before the ball was about to hit their paddle, it would just vanish.
And this is where it gets totally mind-bending. By scanning their brains, the scientists found that to hit the invisible ball, the monkeys were running their own little physics simulation inside their frontal cortex. They were predicting the ball's path in their own minds. And that internal world model is exactly the kind of thing researchers are trying to build into AI.
So we've seen how scientists are trying to copy the brain and use virtual worlds to test their ideas. But what's the end game here? What's the ultimate goal? Trust me, the ambition is way bigger than just building better robots or smarter chatbots.
So what can we expect soon? Well, in the next 2 to 3 years, the aim is to create agents that can learn continuously, on their own, for long stretches of time. Now, the Holy Grail, a perfect, detailed simulation of a human brain, that's probably a century or more away. But we don't need to get all the way there to make some absolutely incredible progress.
And the long-term goals? They are nothing short of profound. The first is to build agents that learn for their entire lives, just like we do. The second, by copying the one system we know is conscious, is to finally get a scientific grip on the mystery of consciousness itself. And the third, well, maybe we can build entirely new kinds of intelligence that can help us tackle the deepest questions about the nature of reality.
And that leaves us with one last big thought. For centuries, we've tried to understand our own minds just by looking inward. But what if the only way to really solve the mystery of what's going on inside our heads is to build one from scratch? The next time you think about what makes you, you, just imagine if we could one day build a machine that could help us find the answer.